everyone, and welcome to That's Absurd. Please elaborate. I am your co-host, Trace Dominguez.
And I'm also a co-host, Julian Huguet. This is the show where we take absurd, silly, ridiculous, far-out questions that maybe we've always wanted to know the answer to, or some of you may have even asked. We research them, we dive in, we come back, and we share our findings with each other. And this we've got some pretty heady questions I'm looking forward to tackling.
This one's going to be a big one, so I hope that y'all are buckled up and ready to go, especially if you're listening in the car. Always wear your seatbelt.
Yeah.
We like to, before we get into our questions, ease into it with a little bit of science news. If something was stuck in our brain this week. Did anything get stuck in your brain this week?
Funny you should say specifically stuck in your brain, because it's a story about something being stuck in someone's brain, sort of, and spinal column.
What?
I know.
Wow.
Well, on our last episode, we had a listener question about a shared collective consciousness, and we talked about maybe there'd be a way to technologically kind of bridge thoughts among humans. And then lo and behold, a big science news story that's going around right now is about a man who had suffered a cycling accident and was paralyzed from the waist down, who, through the use of Bluetooth technology and implants, is able to move his legs again. Yeah.
Whoa.
I was like, this is the thing we were just talking about.
And what I mean, that's one of the, goals of this whole field.
I know. Big hashtag goals. I feel like that's reducing it way too much, because this is huge and, potentially life-changing. But yeah, there was a man from the Netherlands named Gert Jan Oskam. I'm sure I butchered that. I'm so sorry.
Sorry, Gert.
He has been partaking in some research with some Swiss scientists, some Swiss-based neuroscientists, and they have basically connected a Bluetooth implant to his spine, below the brain, and they read his brain waves with some electrodes on his head, and they can actually detect when he's having the thought pattern of I want to move my legs, and then it transmits it to the Bluetooth, which then sends it along the neurons and gets him to actually move his legs again.
That's amazing.
It's incredible. It's very mechanical. Of course, there's videos of it that you can watch and see him pushing along. He's got a stroller to hold himself upright. But yeah, he's just motoring his feet along. And even more insane, he still has some connection between the neurons in his spine and his brain, and he's had some movement recovery without the implant active now.
Just to because he's been thinking about it so much, his nerves are coming back?
Yeah, and it's being stimulated, so he's able to also kind of stand up on his own without it. It's just incredible. But in the context of our conversation, I thought of hey, if you really wanted to try this whole hive mind thing, this seems like an important step on the way there.
I mean, important step, Julian.
Sorry,
important step.
I can't help it.
Julian.
I can't help it.
Well, you could help Gert, okay?
I could.
He needs it.
It's incredible news for Gert Jan.
I'm so proud of him. Congratulations, Gert.
Fantastic.
That's so cool.
I know. We've got a lot to talk about.
I know. We should dive into this.
We really should. Do you want to go first, or shall I?
Who went first last week? I think you did. So I'll go first this week with the very easy to describe question that we got from a 5-year-old listener from Canada.
Wow.
I know. His mom was listening, and she DM'd me on Instagram and said, my 5-year-old has a question.
My name is Matthew and I live in Canada. How long would it take to make a Lego replica of the sun?
Wow.
And I was like, I have to answer this question.
Is a good one, yeah.
So this one is really, really exciting. There's some math in this, warning. Warning.
No.
But it's going to be really good. So what are your initial thoughts? I want to know before I dive into my answer.
You and I are both lovers of brick-based educational toys.
Yeah.
Let's be real. We can call them models or sculptures. They're toys.
Yeah.
But I can't help myself. I absolutely still throw my money at that Danish corporation every time they release something new. They just came out with a Pac-Man.
I know. And you can play it.
Anyway.
Take all my money.
So having a lot of familiarity with that, I think this is going to be pretty eye-opening on just how freaking enormous the sun is.
Yes.
It's so large, and I'm imagining building it out of the classic 2x4 Lego element. And I think it's going to be an utterly absurd amount of time.
Yes. I'm just going to tell you, you're totally right.
Okay,
it is an absurd amount of time. I didn't choose the 2x4, although just to make it a little more fun. So I sort of just had to pick something and run with it. The 2x4 was my first thought. The thing about this question is it really comes down to a few different things. The first thing is we need to know the thing that we're replicating, the sun. We need to know the bricks that we're using. So you mentioned 2x4s. I didn't pick that, and I'll tell you why in a second. And we need to do the math. And the reason I didn't use the 2x4 brick is because the bricks are kind of complicated. They're not squares. So let's go with the bricks first, because we're already talking about it. Quick sidebar. I failed calculus.
Okay.
I'm not super always confident in my math skills. I love math, but I don't always know if I'm good at it. I want to put a big old asterisk on all my math, and I always try and double check it as best I can, but I hope I didn't miss math this. Yeah.
You hope you didn't miss math.
I didn't want to miss math. So a 2x2 square brick is only a square from the top down. From the side, it's actually slightly shorter. So its dimensions are 15.2 millimeters by 15.2 millimeters by 12.7 millimeters.
Okay.
So it's just slightly shorter.
We're not a perfect cube here.
Right. And so the reason I bring up the globe set is because how it got around this problem that it's not actually a symmetrical brick is you build a skin of flat plates. And those flat plates taper as they get near the top, and they get wider as they get near the middle.
Okay.
Now that works if you're building a set with an internal structure. There is a Lego model, which you can see the box right here in the room because I just built it not that long ago, of the Earth. It's a globe model.
Yeah.
And so I took inspiration from that. Because what happens is in the globe model, if you're not a Lego person, all Lego system blocks or Lego bricks can work together because they're all uniform in size. The studs are the same. The depths are the same. So what we're assuming here is rather than building the entire sun out of an internal structure and all of these pieces, because you'd have to use thousands and thousands of different piece types in order to make everything work together, I tried to keep the math as simple as possible and give us an extremely rough estimate of just how to build the skin part. So just a plate, flat, 1 plate thick, a 10 stud by 10 stud square.
Okay.
And so I calculated it based on that because it's a symmetrical piece that we don't have to care that it's not symmetrical in height. And it makes the math a lot easier. And this is a complicated problem that even people who are Lego creators work with, which is that, and luckily for me, people who are smarter than me have come up with something called the LDU. Do you know what an LDU is? Because I didn't know what it was.
No, I think I think my college hockey team lost to them in the semifinals. No, what's an LDU?
So there's a software program that people use when they develop Lego creations, so they don't have to actually go get the pieces and build them. They can get pull from a digital library, and the LDU is called a Lego Draw Unit, and it's a way to convert all Lego pieces, all of them, into integer sizes. So a 1 brick width or depth is 20 LDU. A 1 brick height is 24 LDU. 1 plate height is 8 LDU. 3 plates equals 1 brick. And so it becomes integers, which makes it much easier to work with.
Gotcha.
And so just put a pin in that for a second. So we're going to use a 10 by 10 plate. We're not going to be concerned with gaps because you can't fill every gap. Even the globe model doesn't do that. We're not going to use curved plates because even though those exist, even, again, the globe model doesn't do that. It gets more complicated. And we're not calculating the internal structure only because the amount of pieces required and the complications of those pieces that you could write a PhD on.
You're just doing the surface area of the sun, no structural support on the interior.
Yeah.
Filling up the volume. Just the outside.
Just this, yes, exactly. The skin of the sun, so to speak.
Okay.
And the reason we're doing that is because we're trying to figure out how long this is going to take.
Okay.
So we can start there and see what that calculation is. And then if we need more calculating, we can work our way toward the answer. I don't think we'll need more calculating because it's a ridiculous amount.
Okay.
So the second thing we need, now that we know we're using 10 by 10 thin plates, we need to know the surface area of the sun, as you just mentioned.
Right.
The sun is a miasma of incandescent plasma, which means it doesn't actually...
nuclear furnace. You have to let me finish.
I'm sorry, I'll do it again.
Giants lyric.
So it's neither a gas, nor is it on fire, nor does it actually even have a surface. However, there is a point that we genuinely think of as the surface of the sun.
Yeah, it's the point where you touch it and you go, hot, 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 hot.
Even my toddler knows that.
Hot, 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 hot.
So the sun is this giant collection of hydrogen and helium, and it's so big that
How big is it?
And unfathomably big. It's about 12,000 times the area of the surface of the Earth. Which is pretty
big. That's a big number.
Yeah, it's about 6 trillion square kilometers. So remember, we're working with a 10 by 10 plate.
Which is, how many square kilometers is that, Trace?
Quite small.
It's not any square kilometers.
Yeah,
it's a very small number of square kilometers.
So if we combine this information, 6 trillion square kilometers, with a 10 by 10 Lego plate, we have to be using the same units. So we'll convert that 10 by 10 plate using LDU. So knowing that a 10 by 10 plate is 200 LDU, and 1 LDU equals about 0.4 millimeters.
Man.
So one 10 by 10 plate is about 64 centimeters squared, or 8 centimeters on a side.
Okay.
So that totally makes sense. And in fact, having handled these, I can actually picture like 8 centimeter plate. It's pretty small.
I'm trying to get in my head to the math of from square centimeters to square kilometers.
Yeah.
So a square meter is going to be 10,000 square centimeters.
Yeah, I think so.
And then multiply that by 1,000 times 1,000, so 1,000,000.
Yeah.
So it's going to be 10,000 million. So 10 billion.
More.
Wait, what?
You divide the area of the sun by the area of that, or, divide the 10 by 10 plate into the area of the sun, and you end up with 9.375 times 10 to the 20th pieces.
Oh, I was just going centimeters to kilometers.
Oh, yeah.
I just wanted to get the math right.
Sorry, we're going even further than that then. That's how many pieces you need. 937 quintillion 500 quadrillion bricks or plates.
The 10 by 10 plates.
Yes.
Quintillions.
Quintillion.
So you got billion, trillion,
yep,
quadrillion,
yes,
quintillion.
Right.
How many zeros is that?
It's 9.375 times 10 to the 20th.
Okay.
So
quite a few
zeros.
9 and then 20 zeros after it, and then plus more.
Yeah, with some change. Change there. Just a bit of change.
Just a few more plates.
That's
that you
a lot
pick
of
up
bricks.
At the Lego store.
That's a lot of bricks.
Yeah.
So at 937.5 quadrillion bricks.
That's before you get to the bricks connecting them.
Yeah, that's why I didn't do that math.
No.
I just started with the skin.
You're just papering over the sun.
Yeah, with bricks.
And you've got 9.3 quintillion.
ABS plasticking over the sun.
Yeah.
Really. But yes, it's yes.
Point stands.
Right. So, in order to know how long it would take to do that, we need to know how many bricks we make per year.
You're not thinking assembling. You're now thinking manufacturing.
Yeah, we got to start at manufacturing. We need the bricks. You can't just snap your fingers and have 937 quintillion bricks. So we make 60 billion Lego bricks per year currently. And so at 60 billion, it would take, any guesses?
I can't do that. No, there's too many zeros. I can't do
3.5 times the age of the universe.
To make.
To make at 60 billion a year. That's just to make the bricks. Okay. We haven't done anything with them yet.
Let's say we pull in parallel universe Earths, though, and we get all of them making, and we've got all of our pieces ready. I did that
ready for assembly. So if you wanted to build that number of bricks required in a human lifetime, you would double the production to 120 billion, and then you would multiply that by 1 million.
Okay, sure.
And then you're making 12 million trillion bricks per year, and then it would only take 78 years, a month, and 14 days to make the bricks.
Easy.
Yeah. And that gives you plenty of time to launch them all into space in order to start building.
That's a good point. Yeah.
Or, I mean, I guess you could start building them like on the surface of the Earth and slowly, build out. That would be fine.
Yeah, just stack them really high.
You're really going to just do that. So, I'm not an expert in ABS plastic production. Maybe, that's a lowball number, and producing 12 million trillion flat 10 by 10 pieces could be done really easily. ABS plastic is just a polymer, so it's carbon and hydrogen and a little bit of nitrogen. We have plenty of that. So it's just figuring out how to get it all and put it together.
Yeah, we'd have to divert all human manufacturing efforts to this task.
Yeah, easy.
Everything on the planet would have to be like, listen, everybody stop the wars.
Our Canadian listener needs this
Stop
done.
Whatever you're doing. There's a 5-year-old in Canada who by the time he's 83, we need to make sure he can cover the sun in plastic. Chop, chop.
He wants to build a Dyson sphere that is exactly the size of the sun. So now we need to build it.
Great reason why the whole Dyson sphere concept is patently absurd. I know sci-fi loves it.
Yeah.
But come on.
I know. It's just ridiculous to think about. We haven't even started building it yet. We're just getting the pieces up.
Yeah, we're at this point, we're opening the box and pouring out the bag. Yeah, we're knolling right now.
We did the knolling. I think we've knolled at this point. So now we're building the sun.
We're knolled, we're ready to roll.
This is a Lego sun. Lego means play well in Danish.
Fun fact.
Leggot. Sol in Danish is sun. So this would be the leg sole.
There's a lot of mispronouncing Danish things on this show.
Yeah, well.
I couldn't get the man who could walk again's name.
Yeah, that's the Nordics we're really having trouble with.
We're not doing well. Okay, continue.
So we start building. You got your 10 by 10 plate. You put it next to, because we're not assembling them on top of each other, that would increase the number of plates required by 20%.
Okay. Yeah. Not to mention it would melt.
Yeah, probably long term. So we're just going to glue them edge on edge.
Yeah.
Just the smallest amount of glue. So we're doing that.
We're pulling out the Craggle from the Lego movie.
Yeah, the Craggle, exactly. So we're starting plate after plate. Start out to be then miles wide to reach the diameter of the sun, which is, if you remember from high school science, it's 109 Earths across. So it's quite, wide, the sun. So after we get to miles, then it's thousands of miles wide. So we're shipping pieces all along the edges, all throughout the planet, until eventually it has to go into space. The construction site would be wide as a whole continent, and then the width of the planet, and then the distance from the Earth to the moon, and then the distance from Earth to Mars. Still, just building and building. We know that from the Apollo and now the Orion missions that it takes between 3 and 5 days to get to the moon. So, that's about 380,500 kilometers.
If you're traveling at an insane speed, not super gluing something and then moving it along one at a time.
You have to ship the pieces to where the building's happening. So if somebody's over there building, we have to get them their pieces so that they can keep building. So as we approach construction of the sun's equator, the width of the actual sun is 1.4 million kilometers. So going to the moon gives us an approximation. Yeah, about a quarter. So the moon is freaking far away, actually, is what that taught me, that the moon is really far because, you're going a significant distance across the sun just going to the moon, if you think of it in just distance. So anyway, somehow we're launching rockets that are just taking Lego plates, and they're going that distance in about a month just to get the bricks to the person at the construction site. It would take a month to get the bricks there. It took us 30 years to build the International Space Station, which, by the way, has the internal volume of a 5-bedroom house. So I think Leg Sol is going to exactly take all of humanity's efforts for a period of a century at least.
Wow.
Just to get the bricks, we can build them over 100 years, and we're just slowly over that time assembling them, and it's just everyone's goal.
But if we're smart about how we're managing this project, right? Where they come off the press and then we turn around and print them. So
I honestly think that the building part is the easy part of this, because it's if humans have proven that we are good at something, it is logistics. It's getting. We produce it and we can get it somewhere. We're really, really good at that when we focus on it. It's the thing that we're probably one of the best it's one of the best things we know how to do.
Yeah.
And
take that, chimpanzees.
Right? So if it came to just like, we don't care about the environment, we don't care about what we're doing to anything. All we care about is building the replica sun out of Lego. Then we could be launching rockets all the time. We could be continuously supplying the lines to make sure that the plates are getting built.
Did you by any chance calculate like what the finished mass of this would be?
Oh, I'm so glad you asked, Julian, because that is the next thing I was going to talk about.
Good.
Yeah. So if we're just assuming we can do everything that we just talked about and that we can get all the raw material to make all the ABS plastic, the bigger issue we're going to run into is the mass of all of these plates. So we, again, aren't attaching the plates to each other because that would just increase all of our problems.
Yeah.
But a 10 by 10 plate actually doesn't exist in the Lego system. Most of the plates are either 12s or 8s. Like I couldn't find a 10 by 10 specifically in the online Lego catalog. But it would be about 14 grams. And what I did is I took a 2 by 10 plate and I multiplied it by 5.
Sure.
So it's about 14 grams. 937.5 quintillion of those plates would be 13 roughly quadrillion metric tons, which is 10 to the 19th. So that's a lot of mass.
Can you put that in context for me?
I can. So that's not even a moon in terms of mass.
Oh, that's good.
Yeah. So everything in the solar system would be more massive than that, but it'd still be quite massive. It's like a large asteroid mass.
You know, what's funny is if it's at this point, we're really going to be struggling with the gravitational pull of other planets and moons and stuff going by, trying to tear our Lego sun apart.
Absolutely. We'd probably have to deal with tides.
Tidal forces, yeah.
Both from our own planet and the motion of that. Like if we started building it on our planet is rotating.
Yeah.
So where it starts on our planet, it's whipping around by the time we get out there.
You'd have to have a movement. It's so stupid. It's so... No,
we couldn't build it anywhere that the moon orbits or the moon's just going to smash into it.
We could put it in like geostationary orbit, right?
Sure, yeah, like a Lagrange point for a while until it gets
100,000 kilometers away from us, right? And then
because it's just so big. So we end up with a Lego model that's hollow, but is so large that the planet Jupiter looks small in comparison.
But because it's hollow and these spikes are so light, it's going to get torn apart
all the time. There's going to be things hitting it constantly.
And
smashing it into pieces
just
again.
Seriously, the other planets, as we go by them, and because we're going around the sun faster than Jupiter. The farther away you get, right, the slower things are going around the sun. Like, we're gonna have this issue of these tidal forces destroying our... See, when this question was first pitched, my thought was like, if it's got an internal structure, right, to support it, that's going to be so massive. My fear was going to be that it would crush itself.
It would, absolutely. Yeah, they can only hold Lego bricks.
Yeah, get it right.
Almost got in trouble there.
Oh boy,
it's like 300 and some thousand.
Because
it's like
I don't know.
Then
if
they start
this,
smushing themselves.
Legos can't be plural because it's actually a portmanteau of two Danish words that mean play well. I don't know.
I've heard that. I don't know where, but I heard it. So they start smushing themselves with their own mass.
Yeah,
and. Because we don't have to worry about Earth gravity, we're assuming we're building this. If we don't build it on Earth, we build it in space somewhere, then we just have to worry about its own mass.
Yeah.
So they wouldn't smush each other quite as readily as they do on Earth, but eventually, yes, they would. Once the Lego mass reaches Earth mass, which it absolutely would, we would run into trouble. Like even before then, they would be squishing each other. And if we built it as a solid thing, even with all the air inside of a 2x4 brick, and it's like 80-some% air. It's like, I think actually 90-some% air I looked up. Even with that, it's like 8% of the mass of a solid thing the same size, you would end up essentially creating a mini sun out of ABS plastic.
Wow.
Because there's just so much mass involved that eventually it would collapse upon itself, which would generate heat, which would eventually kickstart, maybe not fusion, but you can do fusion with carbon. It just would require a lot of pressure and a lot of heat. You can do it all the way up to iron. So it's like you could make some kind
That's
of...
a real Lego replica.
That would just be ABS plastic. It would just break itself into carbon, hydrogen, and nitrogen.
There's also, so you mentioned by your calculations, right, that you would the mass of all the plates would be about that of our moon.
A little less. Our moon is would be heavier.
Okay.
More massive.
If we're taking this off the Earth and assembling it in space, we're reducing the mass of our own planet.
Yes.
By basically one moon.
Yeah, it would be pretty significant amount of raw material in order to make it. I would think that, if we were smart, we would just start harvesting carbon, hydrogen, and nitrogen from other places in the solar system.
To protect ourselves.
And honestly, it might even be closer to the part of things that we're building. Because if you think about it, just the width of the sun alone would be enough. Like a large star, if you just put two of them next to each other, would engulf all of the inner planets and like even up into the asteroid belt. Depending on the size of the star, you could really screw up the solar system building
asteroids.
this.
I forgot about the asteroid belt.
So you go to the asteroid belt. Yeah, you're going to end up with trouble there. So I have a tattoo on my arm, and it's to scale. So if we use this as a rough scale, the sun is 19 centimeters. On my arm scale.
This is how seriously we take this. I'm now looking at your arm as a point of reference.
Right. So now imagine the sun is a beach ball that I'm holding in my hand. Now put a second beach ball next to my arm.
It would take up a lot of
a lot of solar system.
Yeah.
Even hollow, it would have to be built in such a way where like the center of the hole didn't intersect with planets and could maybe be orbiting the sun itself.
It's a lot.
It's a lot.
It's a lot.
It's a great question.
But yeah, so your conclusion, all the other implications aside, is to build the plates required and then actually assemble them, assuming all goes well, about a century?
I mean, assuming that's all we did and nothing went wrong. I think the actual assumption is never.
Yeah.
Because as soon as you start to build it, meteors are hitting it, comets are flying around, asteroids are in the way, planets are in the way. The sun is so big and just so, takes up so much space that if we were to build a replica of it that was solid, we'd be creating a sun. If we build a replica of it that's hollow, it would be smashed apart, pulled apart by tidal forces. It would just be destroyed as we're building it. So I don't know if we'd ever complete it.
So you'd have to basically just be content with your Lego, not 1-to-1 scale replica. Maybe 1 to many, many thousands or millions scale.
Just build the globe set, man.
The globe set's really cool.
It's a really nice set.
I find myself envious of you every time I see it.
It's quite small. It looks nice on my bookshelf.
Yeah.
That's it.
That's great.
I mean, amazing.
I love that question.
I really appreciated the question. It was really fun. One more last kind of thought. The ABS plastic that they use to build Lego has a little bit of flame retardant chemical in it because ABS plastic is slightly flammable. The chemical formula for ABS plastic is C8H8, C4H6, C3H3N, okay? Which means it's basically half hydrogen. So again, if you start to build all of these without the flame retardant chemical in it, you do just create a hydrogen ball with some carbon and nitrogen thrown in for fun, which is basically a sun. So a replica of the sun is a sun.
Oh, fun. A very dirty sun.
A really dirty sun. Wonder what color it would be. Oh, should have figured that out.
Oh, well, you got to make it out of yellow, obviously.
Yeah, right. Yellow pieces. Yellow pieces. Yeah. And maybe a little orange just for fun. Throw a few oranges in there and some yellows. Maybe a few greens because our sun's actually in the green spectrum.
Yeah, I mean, it's the most wavelength, the most light it emits is in green, but then it's, all spread out and emitting all colors. So it's white on balance.
Yeah.
Yeah.
Yeah. Thanks, sun, for everything you do.
Good job, son.
Let's take a quick break and then we'll come back for Julian's question.
Proud of you, son.
Julian, give me your best dinosaur roar.
Oh, God, an asteroid! It's horrible!
Wow, that was not where I expected that to go. We're popping in before the show to tell you about I Know Dino. It's a dinosaur podcast.
You know, we think of those dinosaurs being this thing that's been dead for tens of millions of years. Even so, studying dinosaurs can still teach us stuff that is relevant to the world today.
Yeah, like climate models to help us understand global warming.
Migration patterns of dinosaur lineages, they tell us about Earth's changing continents.
We can also study dinosaur diets, what plants lived then and maybe what animals and how they interact.
And, this is super cool, many dinosaur injuries, paleopathologies, they're the first known occurrences of diseases.
And they talk about all this kind of stuff on I Know Dino. It comes out every week with new dinosaur stories that you're not going to hear anywhere else. Like, I hadn't heard of a lot of these, which is pretty cool.
You can find I Know Dino on Apple Podcasts, Spotify, wherever podcasts are. And if you found us, you can probably find them. Go check them out. And we're back. So our next question, the one that I had to tackle this episode, was also submitted by a listener, actually a person who we've gotten to know. He's been a fan of D News back in the day and Seeker, and I've met him at multiple conventions. His name's Clifton B. He submitted a question, and as a matter of fact, he even recorded his question for us. So let's take a listen into Clifton's question.
Hello, friends. This is Clifton B. I've had this weird question in my head for a few years, but I never really looked into it myself. I always thought someone with a better science brain should be the one to answer it. So you're in a room, and in this room there are 4 buttons labeled gravity, electromagnetism, weak nuclear, and strong nuclear. Now, when you push one of these buttons, its corresponding fundamental force will just magically go away. It'll stop working everywhere forever. What effect will each button have at the astronomical scale, at the human scale, and at the microscopic scale? And as a small bonus absurdity, could life in some form somehow continue with any of these forces not functioning anymore? All right. Thanks all. I love the show.
Wow. Okay, Clifton. You could not have created a more Julian-friendly question.
Yeah, in that I have the urge to answer it, and also I hate myself while I'm doing the research for it, because it's like so complex and over the top. And I was like, we had like a deadline coming up. We're like, let's record Thursday. What do you want to pick? I'm like, that one. And then I was kicking myself, like, why did I pick I always go for the quantum mechanics ones. What am I doing? But I do love it. I do love it. I love the idea of this room with these 4 buttons and each of them are labeled. I love the idea
of it's just that meme with like the 2 buttons and the guy sweating and he's just like, what do I do?
I'm picturing more Homer Simpson asleep at his desk and he wakes up and he's like, electromagnetism, and then he just presses it.
That's a great Homer Simpson impression. I don't think I've heard.
I can't do Homer Simpson. Doe. I think the theme of this show is my impressions get worse every episode.
Honestly, I don't know how they could get worse than they already have gotten.
Okay, we have established I am not Hank Azaria.
No.
I cannot do...
He's a genius.
...any other voices. Doe.
Okay. So, Julian, I have one major question that I want to ask.
Yeah, go ahead. Make my life harder.
Which one of the buttons kills us?
Oh, you want to know which one?
Yeah. Wait. There are 4 buttons?
There are 4 buttons, right? So the 4 fundamental forces of nature are gravity, the weak nuclear force, the strong nuclear force, electromagnetism.
And of course, empathy, as we learned in episode 3 of our show.
Which we will refer to forever is the strongest force of all. No, the quantifiable things that we can observe doing stuff in nature are those 4 things, right?
So which of those kills us?
All of them, Trace.
Oh, man, come on!
Canceling any one of them is catastrophic for the universe as we know it.
Oh, man.
In different and exciting ways. So shall we dive in?
Please, yes.
All right, let's start with gravity, because gravity's the one I think that day to day most of us have the strongest grasp of, right?
Strongest grasp, weakest force.
That's right. It is the weakest of those 4 fundamental forces. It's the oddball out if you're a particle physicist, right?
Yeah.
Because the other 3 are all carried by certain types of particles. Those types of particles, by the way, are bosons. And the idea is like when particles interact, they exchange bosons, and these bosons carry a discrete amount of energy back and forth, and that's responsible for the other three forces.
What we experience is electricity or nuclear whatever, the things that hold atoms together.
So gravity, though, is the only one that doesn't have a boson associated with it, at least not yet.
Yeah, not that we know of.
If you ask a particle physicist, they tell you, like, we pretty much think there's something called a graviton that we haven't found yet, because it's weird that this one force wouldn't play by the same rules as the other three. But if you ask Albert Einstein, he would tell you it's because things with mass curve space-time, and then other things with mass follow that curvature, right?
Got it.
It's why planets orbit around the sun, right? The sun, being so big, as we know, right, curves space a lot, and then our planet just kind of
like
circles
that thing at the
drain.
mall where you put the penny in it and it goes around.
Yeah, until it spirals into the drink. Okay, so let's say we hit the cancel gravity button, right?
Ooh.
Now, on the atomic scale, because that was Clifton's question, right? Of the three, atomic, human, universal. Atomic scale, because gravity is so weak, you can basically kind of cancel it out, right? Other forces, electromagnetism, strong, weak, even the weak force, have more of an impact at the atomic scale. So at that level, particle physicists don't really consider gravity. You have to be at the human scale and bigger in order to notice something. So let's go to the human scale. Okay. If gravity's gone, you would probably almost immediately start floating away from the Earth.
Ooh.
Like, if nobody warned you it was coming and you didn't grab onto something, and like somebody hit this button and you took a step, right? Like, there's an upward component to you walking, to the force, right? Some of it is you pushing on the ground and backwards, and some of it, is you keeping yourself upright and pushing downward. That just lifts you up into the air, and you start floating away.
Wouldn't the air also float away?
Yes, that was my next point.
Oh my gosh.
So the air is only on planet Earth because gravity is attracting all these air molecules down to the ground, right? But here at ground level, they're going to start bouncing off of each other and diffusing in random directions. And so they're going to start diffusing off into space. So yeah, the atmosphere starts floating away as well. It's bad.
Yeah.
Yeah. I think we can expand now to a larger scale, at the cosmic scale. I mentioned the only reason the planets are going around the sun is because of gravity, right?
Yeah.
It provides that force pointing towards the middle of the circle of the orbit, right? Without that, everything flies off in a straight line.
Oh my God. It's almost like you use the thing, you put the penny in.
Yeah.
But instead of being curved, which that curve is gravity, it's just flat. So instead of going around, you put it on the little track, it rolls down the track and just keeps going in a straight line.
Or imagine you had like a ball on a string and you're swinging it around your head.
Yeah.
And the string snaps. What does the ball do? It flies off in a straight line.
Yeah.
Right? So all the planets just... Oh, and our own moon, of course, which is only, tethered to us because of our mutual gravities. We all just fly off. Whatever direction you're going at that exact instant gravity's canceled, you're just going that way now until
forever.
You hit something, right?
Yeah.
Yeah.
Because hitting things still matters.
Yes, that's important. That still counts. And as this happens, the sun explodes.
Ah! Why?
Because the sun...
Oh no, I know why!
Which is a miasma of incandescent plasma.
A gigantic nuclear furnace!
Yes, thank you. See, I waited for you. The sun is basically a balance between the gravity that's compressing everything inward and then the pressure from the fusion reaction at its core pushing back out, right? And that's why the sun is the way it is. And as stars, collapse and die, they'll expand as, like the fusion kicks to a different notch and, blows the... Anyway, if that gravity is just suddenly gone, it would be like, I imagine, if you're pushing on a closed door and then somebody suddenly opens it from the other side.
Yeah.
So all the material of the sun just shoots off into space in every direction as well.
And it's not just our sun.
Oh,
it's everything.
Oh, yeah. So let's go to the galactic level, right?
Yeah.
All the galaxies, the spiral galaxies that we think of typically, like our own Milky Way, they're held together, here's the fun fact, right, partially by the gravity of the stars, mostly from dark matter, right? We've done the calculations, and we've concluded that the mass of all the stars and things that we can see is not enough to hold
a galaxy together.
Galaxies together, even with supermassive black holes at the center. So there must be something called dark matter holding it together, and dark matter, as far as we know, only interacts through gravitational force. Right? So if that suddenly doesn't matter anymore, all the galaxies fly apart in every direction.
Gosh.
It's basically the
Fireworks.
most insane fireworks show you can imagine.
Amazing. You were going to say the same thing?
Yes, I was.
I'm imagining it, and it seems amazing.
It would, yeah. And
this Doctor Who episode where he just parks himself somewhere and watches it
all go
like
down.
when they watch The Last Days of the Earth, you know.
Yeah, if you were in intergalactic space, I imagine it would look pretty cool. Because like I said, at the atomic level locally, doesn't really seem to have that much of an impact. You know,
Right.
You could exist. There's humans on the ISS, you know, where they're in microgravity, and it's not like they can't exist. So if you're in like a closed spacecraft, you know, your air is all contained, and you've got food and water and light, you know, that's cool.
You're not relying on gravity
Yeah.
to do things for you.
Yeah.
Yeah.
Until, of course, you know, you run out of power because, like, let's say you're on a ship with solar panels, and now because all the stars have torn themselves apart,
There's no solar panel
Yeah,
power.
so you wouldn't get to hang around for too much longer, but it
Right.
would look cool.
It would look cool.
Yeah, so there's that.
Wow.
That's one of 4.
That's one button.
That's the first button.
Okay, wow. I mean, that's pretty spectacular.
That's quite something, right?
Okay.
Okay, so let's move on to the next weakest force, which is the weak nuclear force.
Sure. What does that do?
I think this is probably the least intuitive of the forces because, you know, gravity is, you can conceptualize it pretty easily. Strong force isn't too hard to explain. Electromagnetic force, you're familiar even if you aren't really aware of it. The weak nuclear force, I kind of struggle to explain exactly like a metaphor for it, but all it does is it takes the things that atoms are made up of, right, that protons and neutrons are made up of, and it changes them fundamentally. Right? So protons, neutrons, right, they're not the smallest building blocks of atoms. You can go a layer below that and you have quarks.
Right.
Quarks come in different what are known as flavors, right? There's up and down, charm, strange, top and bottom.
Yeah.
And so these quarks have fractional charges, right? Like an up quark is a 2/3 positive charge. A down quark is a negative 1/3 charge. So if you put 2 up quarks and a down quark together, hold them together, that makes a proton. You get a net charge of +1, and you get your little proton building block. And then
the weak nuclear is what's holding them together?
No, that we'll get to that.
That's confusing.
The neutrons, right? If protons are 2 ups and a down, neutrons are 2 downs and 1 up. So you've got a neutral charge, and you've got something with almost the same exact mass as a proton, but no charge. These particles can decay into one another, and they do so via the weak nuclear interaction, okay? So when a proton turns into a neutron, it gives off a boson. We talked about these force-carrying particles, right? It gives off a W plus boson because it loses its positive charge, it becomes neutral. Something has to carry that positive charge. That's the W plus boson, and then the W plus boson decays into a positron, which is like the plus version of an electron, and a neutrino.
Woo, this is complicated.
I know. Hey, particle physics over podcast. I'm sure it's really easy to grasp. And the neutrons are the opposite. They will emit a W minus boson, and that will decay into an electron and an antineutrino. I know it's all complicated, but this weak interaction is responsible for some pretty cool stuff and some pretty important stuff. The carbon-14 dating, when we figure out how old stuff is, that's from carbon-14 decaying. One of the protons in carbon-14 decaying, and it turns into another element.
And we can use that because it happens at a specific rate.
Exactly.
So we can use that to measure how long something's been around.
Right. So on the flip side, the weak interaction is essential to nuclear fusion, the process that powers the sun.
Oh, no.
Yeah.
So let me just see if I get this straight. If you hit the button, then the atoms don't decay the way they're supposed to.
That's right.
But there's also no solar fusion. There's no fusion, period.
Yeah.
So without that, again, everybody dies.
Yes.
And the universe kind of just... But instead of fireworks, it seems like it would just be like...
Not with a bang, but with a whimper.
Yeah. It would just be like, I'm done.
Yeah, I think that's fair. I mean, I'm no expert, but
sure.
Fusion in the sun happens when hydrogen atoms are colliding into each other, right? And hydrogen in plasma, it's just protons whizzing around, right?
There's no electrons. They've all been stripped away by the hotness.
Yeah, but stable helium needs 2 neutrons, right? It's 2 protons and 2 neutrons because the neutrons provide stability to the nucleus. So when these protons are colliding into each other, some of them need to turn into neutrons through the weak interaction. And that is what enables fusion to happen and energy to be given off and light to be given off. So yes, without the weak nuclear force, you can't have stable elements through decay, like some of the heavier elements. And as far as I understand it, fusion in the sun wouldn't be able to continue.
Wow.
And then if we haven't canceled gravity, then gravity would take over and crush the sun.
Oh,
remember I mentioned the balance of forces?
Because you're only turning off one. So Earth is still here and the mass of the sun is still the same.
Yeah.
So we're still in orbit, but the sun is now imploded upon itself.
Yeah.
Which would increase heat.
But there's no way to do fusion.
Oh, wow.
Yeah.
No idea.
So you just crunch your sun into a little brown ball. That
would it become a black
dies
hole
off.
then?
I don't think it's got the mass to become a black hole. There's a certain limit.
It wouldn't give off light.
No,
heat,
it wouldn't.
So it'd just be a little golf ball.
Yeah, there are like
I mean, not literally, but
dwarf like
brown dwarfs and things.
Yeah, those are like the remnants of stellar cores that didn't have enough mass to collapse on themselves and become black holes, but they also couldn't sustain fusion any longer, so they just fade.
Yeah,
eventually, but it's not the same as a black hole.
Good model for this. Either way, bad. But not as spectacularly bad.
Yeah. So let's talk about the electromagnetic force now.
Okay. I'm excited for this one.
Okay.
This one's my favorite.
So this one, you probably know the boson that carries the electromagnetic force. It is...
the electron.
No.
Yeah, I know.
No.
It's obviously the neutron.
No, that's incorrect again. The boson...
Oh, right.
The boson that carries the electromagnetic force is the photon.
Oh, of course, I knew that.
Right. So we think of them as like the light particles that we can see, and that is true, but they also are what carries the electromagnetic force in general. So things with charges either attract or repel, right? If you've got like charges, they repel each other. Unlike charges, positive and negative, they attract each other, right? And this is carried by photons, both real or virtual. So in an atom, right, you've got a positively charged nucleus where the protons and neutrons are, and then they're orbited by these electrons. The thing holding that stew together is these virtual photons that exchange the electromagnetic force between protons and electrons and keep the electron orbiting around the nucleus. So, Trace, what do you think happens if we eliminate the photon?
I feel like at the atomic level, we're going to get quite a show.
Yeah. All the atoms, all the electrons and nuclei dissociate.
They just fly apart. I guess it would be analogous to turning off gravity. I mean, assuming at quantum mechanic levels they behave the same, which they don't. But it'd be like the electron would just whiz off in some direction.
Yeah, exactly.
Based on quantum mechanics, and it probably wouldn't literally whiz because they don't even really exist, but that's fine.
That's all just waves.
Yeah.
It gets confusing at this level.
Yeah.
Anyway.
So, no atoms, which means, but that would happen instantaneously. So at the human level, I'm guessing we just disappear.
We just Thanos crumble into...
But without the dirty leaves. It's literally just like poof. But
atomic
no poof,
dust.
Because there's no wind.
Right.
Huh. Well, I guess at the human level, we're not saying the energy dissipates. So, the energy might still be flowing in that direction. There would just be no particles to carry it.
I can see the consternation on your face.
I don't like it.
The way I imagine it, right, is like all these atoms that are held together because of photons, because of this electromagnetic attraction, just dissociate. So any bonds that are reliant on that, right, like ionic bonds or covalent bonds, right, those are all undone. Anything that relies on charges and the forces that moving charges and magnetism apply to things, that's just gone. It spontaneously disassembles, and you've got basically a bunch of swirling nuclei and electrons whizzing around with no order anymore.
That don't like each other anymore.
Yeah.
And find any way to get along.
Yeah, and there's no reason, right, like that when nuclei are traveling along now in our space, right, the positively charged nuclei don't repel each other, anything like that, right? They're all just randomly colliding and moving around.
Oh my God,
now.
we end up with like a particle soup.
Yeah.
Like a early universe situation. Post Big Bang.
I'm so glad you said that.
Really?
Yes, because here's a fun fact. It is particle physicists have shown that the electromagnetic force and the weak force that we just talked about at a high enough energy level, like in the early universe recently after the Big Bang when you had crazy high energy particle soup, they're actually the same force.
Oh, cool.
Yeah. So they unified them into the electro-weak force, and then as the universe cooled, they kind of split off and do their own thing. But at high enough energy levels, they're the same force. So I like to imagine, as a matter of fact, if you turn off the electromagnetic force, you also turn off the weak force, and vice versa.
Because they're basically the same.
Because they derive from the same force,
we just think
as far
of them
as we know.
as like different things because we live at our current temperatures.
Yeah. Now, because of that, scientists are trying to unify all the forces because there's, we believe the electromagnetic force and the weak force are derived from the same thing. Now we're thinking, probably all forces come from the same one greater force, whatever it may be. We're still working on
clearly the force.
The force. Exactly.
Yeah.
So, anyway, particle soup is bad.
Yeah.
Finally, let's talk about the strong force, which is the strongest force, right?
Yeah.
So we talked about how the protons in nuclei, normally they would repel each other because of the electromagnetic force, right?
Right.
But the thing that holds these positively charged protons together is the strong force.
The thing that holds the quarks that you mentioned earlier together.
That's right. Well, so it's holding nuclei together, the protons and neutrons. It stitches all of them together. And then within the protons and neutrons, the strong force is also the force that holds the quarks together.
Got it.
See why I structured it this way? So
I do.
Can talk about all of them. So the strong force, by the way, these gluons are also kind of in like a gluon soup. Mm-hmm. Tons and tons of energy is actually stored in these bonds. As a matter of fact, the quarks that make up protons and neutrons are a tiny, tiny, tiny fraction of the mass, the overall mass of the proton and neutron. And the gluons, the energy from the gluons is most of the mass. Because if you remember, at the atomic scale, mass and energy are related.
Yeah.
Right? E equals mc squared, right?
MC
energy
squared.
equals mass times the speed of light squared. And so when we do things like nuclear fission, when we split apart an atom, the resulting two new products, right, in the nuclei and the neutrons or whatever that come out of it and continue nuclear fission, like in an atomic bomb, the reason that they are less massive is because they are not held together, and that binding energy that held them together is the source of the explosive energy that's released in an atomic blast. Mm-hmm. Okay?
Got it.
Let's imagine we turned off the strong nuclear force. Everything disassembles to a greater degree than if we turned off the electromagnetic force with a gigantic thermonuclear explosion.
So again, fireworks.
Yeah, except this time there's no safely hanging out in your TARDIS with a cup of tea, watching it all burn.
And your companion. Don't forget the companion.
You're part of it. Whether you like it or not.
I guess that's true.
You are part of the gigantic, rapid release of energy that destroys everything in the universe.
Wow.
Yeah.
So to recap, gravity.
Bad.
Fireworks.
Yeah.
Weak nuclear.
Fizzle.
Then electromagnetism.
Dust.
Thanosian dust. And strong nuclear fireworks again.
Yeah.
But, really.
Involuntary. Like
a lot. Like, wow.
Mandatory participation.
Like the finale part.
In the
when
fireworks.
They break out the 1812 overture kind of part.
And everybody just every single person is a hydrogen bomb.
Okay, I have a question then. Inspired by that, if you were gonna hit a button, which button would you hit? And what song would you listen to while you hit it?
Ooh, I mean, it depends on how mad I am that day.
Sure.
Right? If I woke up and it's like, this is really dating myself, but, Limp Bizkit, if I'm just like, just one of those days where you don't want to wake up.
And then what button do you hit?
And then if I'm in that mood, man, strong nuclear force has got to go.
Blow it all up.
Yeah. But if I'm like, just like kind of sad, just
you're
like a
listening
little
to
depression.
some REM.
Oh,
you're just like
some Death Cab for Cutie.
Yeah. Then definitely that's a weak nuclear day.
He would totally write about this. Death Cab for Cutie's got a big nerd streak to him.
Yeah.
Benjamin Gibbard. He's not Death Cab.
He's not personally.
His name is not Death Cab for Cutie.
That's how it works as musicians, though. Like Blondie is not. That's not the name of the person.
Hootie and the Blowfish. Have you seen that? It's like there's a sketch where Darius Rucker is performing and the band is like, bring out the Blowfish. And he's like, I'm not Hootie and they're the Blowfish. The band is just Hootie and the Blowfish.
That's just what it is. This is the name of the band.
Anyway, but yeah, I would probably go weak nuclear force if I wanted some melancholy.
Sure, yeah. Just like...
And then if I had a TARDIS and wanted to impress a date, probably Gravity.
Yeah.
Take her out somewhere nice and be like, check this out. And then,
that'd be cool.
Yeah, destroy everything and be like, okay, now we'll go back in time and fix it.
Yeah, it'll be fine.
Yeah. So thanks, Clifton, for making me do a bunch of diving into particle physics, which is, I'm getting better at it because I've done it so much at this point.
I love any time I get to do particle physics stuff. I've been to CERN twice. I'd go again.
And by the way, if anybody listening is a particle physicist and I got anything wrong, you let me know because I think this is a great question. And if we can cover it more accurately, like, awesome.
We will do an update to this.
I would happily follow this one up.
If you've done something, please let us know.
Yes.
You can send us an email or go to our website and contact us, whatever you want.
Yeah.
So please let us know.
And even if you're not a particle physicist, if you're a listener, you've got your own question, maybe a 5-year-old has a good one, maybe you've got kind of a silly one and you want to pretend you have a 5-year-old that asked it, please let us know.
Yeah, you can do that at that'sabsurdshow.com, or you can check the show notes for a direct link. You can also find links to our social medias. You can find the show anywhere that you get your podcasts. So if you're listening now and you liked this episode, follow us, give us a rating, shoot us a like, whatever it is that you need to do to tell other people that the show is good and you like it. Be our strong force.
Aww.
Yeah.
Hold us together.
Yeah. This episode was edited by Kyle Sisk, and we want to again thank our question askers, who are a 5-year-old in Canada
and Clifton B.
Thank you so much for submitting those questions, and thank you so much for listening.